A government lab in Maryland just filed a patent that engineers have been trying to file for 50 years. Not for a better fridge, for the end of the fridge as we know it. Here's the strange part. The part that does the cooling isn't a gas. It isn't electricity either, not directly. It's a piece of metal about the width of a pencil that gets ice cold the moment you stop squeezing it. You've actually felt this effect before, with your own hands. You just didn't know what you were feeling. By the end of this video, you'll know exactly what that metal is, why it took 2 centuries to make it work, and why the company that finally cracked it isn't trying to sell you a fridge at all. Stick around, because the reason this matters has almost nothing to do with your kitchen. There's a machine running in your house right now that hasn't meaningfully changed since before the Civil War. It's in your kitchen. It's also in your car, behind the counter at every pharmacy, in the truck that delivers your groceries, and in the wall of every hospital that keeps vaccines alive. Pull it out of American life completely, and the country doesn't limp along. It stops. Food spoils in days. Medicine goes bad in hours. Large parts of the map become unlivable for a third of the year, and almost nobody can tell you how it actually works. Here's the short version. A machine squeezes a gas until it's hot, lets that heat escape into your kitchen, then lets the gas expand somewhere else, and expanding makes it cold. That cold gets pulled into your fridge. Repeat forever. It's clever. It's also got 2 problems nobody's fixed in 150 years. Problem 1 is mechanical. Somewhere inside every fridge is a compressor, a small engine with moving parts, pumping thousands of times an hour, every hour, for years. That's the hum you hear at night. It's also the reason fridges die, moving parts wear, seals fail. One day the hum stops, and a $2,000 appliance becomes a metal box. Problem 2 is worse, because you can't hear it. The gas inside that loop is a refrigerant, and refrigerants leak. Not dramatically, just a little, at every joint, every service visit, every time a unit gets scrapped instead of properly recycled. One of the most common refrigerants in American homes traps heat in the atmosphere over 1,000 times more effectively than the carbon dioxide coming out of your car's tailpipe. Now multiply that by every fridge, every AC unit, every walk-in freezer in the country. The US government has already admitted this is a problem. There's a federal law on the books right now, signed in 2020, requiring these high-warming refrigerants to be phased out by 85% over the next decade and a half. Here's what almost nobody talks about. The law passed before anyone had a real replacement. America legislated itself into a corner. It promised to walk away from the exact chemical the entire cold chain depends on, without anything ready to take its place. Which forced a question nobody wanted to ask out loud inside a boardroom. What if the fix isn't a better gas? What if it's no gas at all? Try something right now. Find a rubber band. Stretch it fast. Hold it against your lip. It's warm. Now let it snap back, and press it to your lip again. It's cold. Distinctly, noticeably cold. You just ran a refrigeration cycle using nothing but your hands. That's not a party trick. It's real physics, and it's old. An English scientist named John Goff noticed it in 1805. Decades later, James Joule worked out the math behind it. Stretch certain materials and their internal structure snaps into order, and that ordering releases heat. Let them relax, and the structure falls back into disorder, and disorder pulls heat back in. No gas, no leak, no compressor. Just a material that goes cold the second you stop pulling on it. For over 100 years, that's all it was. A curiosity in a physics textbook. A rubber band degrades in weeks. Nothing existed strong enough to do this trick millions of times without falling apart. Then, in 1959, In a Navy lab in Maryland, somebody wasn't even trying to solve this problem. They were trying to build a better missile nose cone. The researcher's name was William Bueller. He was mixing nickel and titanium at the Naval Ordnance Laboratory in White Oak, Maryland, trying to make a metal tough enough for aerospace use. What he made instead was something nobody in that lab had ever handled. Bend it and it snapped back to shape. Heat it and it remembered its original form and returned to it on its own, like the metal had a memory. They named it for where it was born, Nickel Titanium Naval Ordnance Laboratory, nitinol. Today it's inside millions of heart stents. It's in eyeglass frames. It's in aerospace hardware you've never seen. But the property that mattered most in that first decade sat unused because nobody had a use for it yet. Squeeze nitinol, and its internal structure snaps into a tighter arrangement, and it heats up. Not by a fraction of a degree, the way most materials do, by tens of degrees. Release it, and it drops just as fast, pulling heat out of everything it's touching. It's a rubber band with the strength of aerospace-grade metal. It's a refrigerant you can hold in your bare hand. Years later, when the Department of Energy ranked every possible alternative to the compressor, this effect, called elastocaloric cooling, came out on top. Not near the top, first. So here's the obvious question. If the material's been sitting in a lab since 1959, and the government ranked it number 1, why isn't there one of these in your kitchen right now? Because for 50 straight years, every single machine anyone built out of it tore itself apart. Here's the instinct every engineer had. You take a thin strip of nitinol, stretch it, let it snap back, harvest the cold. It works. It works beautifully for a few thousand cycles. Then it starts to fail. Think about what pulling on metal actually does. Every material has tiny flaws, microscopic voids, rough spots, weak points along the grain. Pull, and those flaws open slightly. Release, and they close. Pull again, and each cycle widens the crack a little more. It's the same reason you can snap a paperclip by bending it back and forth, even though you could never break it with one pull. Metal doesn't usually fail from force. It fails from repetition. Now think about what a real refrigerator has to survive. 10 to 15 years of continuous cycling. That's not a few thousand cycles. That's tens of millions of them. Early prototypes were failing in weeks. Researchers would build something genuinely elegant, switch it on, and watch the exact component doing the cooling develop hairline fractures until it sheared apart. And there was a second problem stacked on top of the first. Triggering the effect at all takes enormous force, which meant a heavy mechanical drive system, which meant most of the energy you spent straining the metal never came back as usable cold. The efficiency numbers were embarrassing next to a compressor that had a 150-year head start. By the 2010s, elastocaloric cooling had a reputation in the field. Gorgeous physics, hopeless engineering, a technology that could impress you in a lab and then tear itself in half on the way to a product. Then, a team back in Maryland, a few miles from where nitinol was born, asked a question that sounds almost too simple to matter. What if we stop pulling it? Researchers at the University of Maryland, working with the Department of Energy's National Lab System, had spent years fighting this exact fatigue problem, so they understood it better than almost anyone alive. Their insight came down to direction. Cracks grow under tension, pulling forces flaws open, but push on that same metal, compress it instead of stretching it, and the physics flips. Compression presses those microscopic flaws shut instead of prying them open. So instead of thin strips being pulled apart, they built bundles of nitinol tubes and drove them in compression, squeezing them lengthwise with hydraulic force. Same phase change, same heat released and absorbed. A completely different failure story. The results, published in the journal Science, didn't just survive longer. They ran with a coefficient of performance far beyond anything elastocaloric cooling had ever hit before, into range where this stops being a lab curiosity and starts being a real competitor to the compressor. Picture the actual machine, a bundle of thin nitinol tubes, arranged like the barrels of a revolver. A hydraulic driver compresses them. As they compress, they heat up, and a loop of plain water, the safest working fluid on the planet, carries that heat away. Then the driver releases. The tubes snap back toward their remembered shape, go sharply cold, and that same water loop carries the cold into your fridge. No refrigerant gas, no chemical with any warming potential at all. If the entire system ruptured in your kitchen, the damage would be a puddle on the floor. And because it's driven in short mechanical strokes instead of running non-stop, it doesn't need to hum through the night the way your fridge does now. Here's what the Maryland team realized once the fix actually worked. They hadn't built a better refrigerator. They'd built something far more general, a way to move heat, anywhere, without gas, without a running motor, without a leak risk. And that lands at exactly the moment the country needs it most. Right now, data centers running AI workloads in Virginia, Texas, and Arizona are straining regional power grids, and a huge share of that electricity isn't computing anything at all. It's cooling. Some facilities burn through millions of gallons of water a year just to keep processors from overheating in states that don't have millions of gallons to spare. Electric vehicles have the same problem at a smaller scale. Every fast charge dumps heat into the battery pack, and heat is the single biggest factor in how long that pack survives, or whether it survives at all. A solid block of nitinol doesn't care if it's cooling a suitcase-sized unit or a deck of cards-sized one. You can bolt it directly onto a battery module. You can bolt it directly onto a server rack. That's the difference between an appliance upgrade and a platform, which is exactly why this is now a funded national priority, not a science fair project. Now, the part most videos like this skip. What Maryland built is a prototype, a genuinely impressive one, but a prototype. There's no date where you walk into an appliance store and buy one. The obstacles are specific. Nitinol isn't cheap. It has to be melted under vacuum, and the nickel to titanium ratio has to be controlled to a fraction of a percent, or the whole temperature effect shifts. A compressor is a commodity stamped out by the tens of millions. A precision nitinol tube bundle isn't, not yet. The hydraulic driver still has moving parts, which means it inherits the exact durability problem the nitinol just escaped, and no manufacturer is going to put this in American kitchens without years of data proving it survives a full-service life under warranty. None of that erases what actually happened here. A wall that held for 50 years came down, not because of a new law of physics, but because one team changed the direction of the force. That's usually what a real breakthrough looks like, not magic, a different angle on an old problem. An American in Massachusetts built the machine that made cold a public utility. An American Navy lab in Maryland accidentally built the metal that might end it. And a university team a few miles down the road finally found the one direction of force nobody had tried. One day you might open your fridge and hear nothing at all. No hum, no click of a compressor kicking on at 2 a.m. Just a box that stays cold because a piece of metal inside it is quietly being squeezed and released, over and over, remembering its shape. So here's what I want to know. The compressor isn't just in your kitchen. It's in your car, your office, the building down your street. If this scales, which one goes silent first? And which one will you actually miss the sound of? Tell me in the comments. And if you want the next one before anyone else, you know what to do.